So first, bonjour, good morning everybody, or good afternoon, depending on where you are. My talk number one. Geopolymer chemistry, geopolymer research started in 1972 when we have been struck by very important fires in buildings in France, and we discovered at that time that plastics in buildings were dangerous. I raised the questions, are organic polymers heat resistant plastic? And the answer is no. Nature states only minerals provide fire and heat resistance. So I set my target, develop inorganic polymers. At that time I was an organic polymer scientist. So geopolymers are polymers processed like organic polymers, and this is the word polymer that you will that you will hear during the entire webinar. Yet they are geopolymers, that is fire and heat resistant. At that time my target was to make a fire and heat resistant material. I had no idea about Portland cement at all, or cement applications. Since they are polymer, they have a polymeric terminology. Otherwise they would not be polymer. Every polymer have a very special terminology that relates to its chemical makeup. So we have here the geopolymer terminology, here for the field of the silico-aluminates, polysilates with SiAl1, SiOAl, polysilate siloxo, SiOAl or SiO, SiL221, polysilate disiloxo, so we have the silate and the disiloxo, and for Si that are higher than SiAl higher than 3 to 1, I introduce the silate link. The applications can be are comprised in various fields. First, of course, fire and heat applications, because by nature geopolymer is fire and heat resistant. Global warming CO2 issue, this is an important issue that is the consequence of the development of the cement and concrete. Environmental technologies is also very important, and we worked a lot on it because it is the ideal material in order to encapsulate toxic waste, radioactive waste. And we have also an archaeological science sections, because I consider that archaeology is providing a data bank for our research, since this type of mineral technology has been used by our ancestors. If we look at the applications, they strongly depend on the chemical makeup, on the ratio SiAl. We have here a three-dimensional network. This is the polymeric character of the molecules, and end up to more flexible material. SiAl1 or SiAl2, these are three-dimensionally very strong networks, and they are used either for bricks or ceramics, for the cement, low CO2 cement and concrete, radioactive waste encapsulation. And then if we increase the silicon amount in the molecules, ratio SiAl 3 to 1, then we enter into the applications, especially very special uses in terms of making tooling prototypes at high temperature for the industry. And then we come up with a higher SI-AL ratios to applications that are really high-tech based, high-tech composite for automotives and aircrafts. The science is to be found in my book, Geopolymer Chemistry and Applications, and this is now the 4th edition. So a geopolymer is essentially a mineral chemical compound or mixture of compound consisting of repeating units. This is the definition of a polymer. For example, silicon oxide, SiO, silicoaluminates, SiOAlO, ferrosilicoaluminates, FAO-SiOLO, or aluminophosphate, AlOPO, created through process of geopolymerization. The microstructure of geopolymers is essentially temperature dependent. It is X-rays amorphous at room temperature, but evolves into a crystalline matrix at temperatures above 400 degrees C. One can distinguish between two synthesis routes. First, in alkaline medium, with the calcium, sodium, potassium, lithium, calcium, and cesium, and the like, and others, and in acidic medium, with phosphoric acid and humic acid. It works wonderfully. Geopolymerization is the process of combining many small molecules that are known as oligomers. This is also a word that you have to learn, into covalently bonded network. The geochemical synthesis are carried out through oligomers that are dimer, trimer, tetramer, pentamer. We will show you shortly after this slide, which provide the actual unique structures of the three-dimensional macromolecular edifice. These are some of the oligomers, aluminosilicate molecules, the oligomers that we find at the beginning of geopolymerization here in potassium silicate solution. This is the orthosilate. This is the first one. This is a very important SiOAl with the OH group. SiOAl2, orthosilate siloxo. And what you see here that in fact linear molecules longer do not exist. They are very fast, become cycles. This is a triangle, SiSiAl, 2 Si for 1 Al, SiSiAl with the Si group, and this one that is a square, that is a very important unit that we'll find in our macromolecular structure, Si, 3 Si for 1 Al. And if we take these molecules, SiSiAl, they polycondense together, build a bigger molecules, that is a ribbon. And you see, we have production here of NaOH. That is, the NaOH will come back into the reactions, and these combine together with others. And this is the stage. At the beginning, we are still in medium that contains some amount of water, and these molecules, if they are heated at a temperature higher than 250 degrees C, the hydroxylates or the OH are evaporated, and we have the formation of silate groups between the system, and it turns into a ceramic material. What are the advantages of geopolymer chemistry? In terms of geopolymer binder and resin, it is water-based, no solvent, no fumes. Water-based, easy to clean with water. It is environmentally friendly. It is water-based, there is no organic solvent, no fumes, no toxic vapor, easy to store, very stable in time, easy to work, no special equipment, safe product, no special protection, not affected by REACH, this is the European standards for chemical product, easy to discard, it is a ceramic-like material. As for composite, they are fire and heat resistant. So we have here a carbon epoxy composite that burns, and a geopolymer carbon composite do not. Oh, pardon. Burns and resist to a flame of 1200 degrees C. As for geopolymer cement, we know that it is calcium carbonate free, low CO2 emission, low energy. We can use byproducts and industrial waste for the production of the geopolymer cements. The fire and heat resistance is very interesting. Here we compare the fire and heat resistance of geopolymer cement with Portland cement. Portland cement, you know that Portland cement explodes above 200 degrees C, whereas the geopolymer, these are geopolymers from the first generations, withstand their strengths up to 700 and 900 degrees C and higher. High mechanical strength up to 100 and more, so we achieved 150 MPa. One of the major property in comparison to Portland cement-based systems, it is acid resistant. You see here the changes in weight with the days, and here same Portland in the same solution. 60% have been destroyed and dissolved. So what are the applications and commercializations? I will only show you some of the applications and commercializations that we are aware of. There are numerous others, and we have the following problem. When I am receiving people from the industry that want to work with us in order to develop a product, at the end of my talk, or our meeting, I'm always asking the following question. If we are successful, will you claim that you are using the geopolymer technology in this new material that we have been developing together? 50% will answer yes, we'll do it, because this is very important, this is high-tech, this is advanced material science. And the other 50% will say no, we don't do it, because by claiming that we are connected to the geopolymer terminology, geopolymer technology, we keep some information to our competitors. So what you see are those who are claiming to relate to the geopolymer technology officially. I have received a lot of questions, a lot of emails, especially for this webinar. I'll just show you one. We would like to ask following questions. Are geopolymer-based products on the market? This is the first question. In which fields of application are they used? List of companies leading the field. A major material chemical company active in the field. The problem that I have with this type of question is that I discover that those who are raising these questions, asking, did not visit our Geopolymer Institute site, because you have the answer there. You have videos, you have news, and so forth. So I am a little frustrated by this situation, and in fact it is something that we discover every time. So we have geopolymer binder, we have geopolymer resins, we have geopolymer paint, coating, grout, geopolymer cement, geopolymer concrete, geopolymer carbon composites, and geopolymer ceramics, only to cite some of the applications. I will present 6 videos on successful application. This is something new in our webinars. Now the system allows us to show videos. I hope that you will be able to really see them clearly. One will show the application of geopolymer binders for foundry, the high-tech carbon fiber composites, one grout for sewage pipes repair, the high-strength geopolymer concrete for airport, and the geopolymer cement commercialization. So here you have 2, 3, 4, 5. In fact, we have 6. Since here we will have also the video that shows my visit to this airport. The first video is coming from the Czech Republic in Europe, from the foundry team, the company saint-quentin. The product is called Geopol. Then we have our sister company Pyramidal System in France for high temperature composites. Then from the US, the company Milliken that has developed, in fact, purchased a company that had developed Geospray. This is a grout for infrastructure rehabilitation. Then we have from Australia the making of the airport by Wagner's. Then my visit to the airport. And the last one, the newest one, from India, Kiran Global Chems Limited, by the second world largest alkali silicate manufacturer. On the pilot scale, this relates to the solidification of radioactive residues and mine tailings, and here it is a special study and pilot production that has been undertaken with a company, a German company called Wismut in eastern Germany near Chemnitz. The company Wismut was from 1945 until 1990, until the fall of the Iron Curtain, the third producer of uranium oxide that have been shipped, that have been transported to the Soviet Union for their nuclear weapons. After the reunifications, they had 6 very polluted mining sites in eastern Germany, and we had been asked by the local government of the land of Saxony to present an alternative to what was known at that time in the solidification and containment of low-level radioactive waste. It is available as a technical paper number 13 in our Geopolymer library. It continues the applications for radioactive waste, and this is here a very more recent one. New geopolymer decontamination tool expected to help Fukushima cleanup. Another one from the Nuclear Decommissioning Authority of United Kingdom that was issued in June 2014. Innovation investment bears fruit. Geopolymer technology could polish up sites, especially by decommissioning nuclear power plants, a unique technology related to geopolymers. Of course, there are applications for the building industry in terms of fire-rated facade material. The well-known world chemical company BASF launched in February 2011 a geopolymer product for the general public, that is a grout for sanitary use. The company Boeing is testing a geopolymer fiber composite made of flax fibers for fire-resistant panels for aircraft interior. Even NASA is testing the geopolymer as glue and other material for airspace. And racing cars are using intensively our system. This is published stuff. So we enter into this high-tech session before tackling the geopolymer cement and concrete. Heat and fire resistant geopolymer pardon, too early. I received an email, I read it. Geopolymer material with expanded glass as filler material. I want heat resistance up to 1200 degrees C with expanded glass as filler material. My answer to this email was, this is impossible because expanded glass is melting. Are you sure you want heat resistance and not fire resistance? He answered, yes, this is fire resistant that I want. That has to be tested up to 1200 degrees C. Why? Generally, people do not make the difference between a fire-resistant product that does not burn, which is the essence of all mineral geopolymers, and a heat-resistant artifact. Suitable geopolymer in general. And suitable geopolymer can in general be subjected to a flame from 100 degrees C to 1400 degrees C without any appreciable change occurring in its properties. But this does not reflect the notion of heat resistance. The heat resistance of a material is a function, in the first place, of at least three parameters: temperature, time, and strength. I show first industrial applications on castable geopolymer where heat resistance is requested. This can be found in my book in chapter 20. If we compare the temperature like we did it for comparing with Portland cement, this is what we have. We have a material that withstands the heat and maintain its resistance at this temperature up to 700 or up to 900. So 110 MPa at ambient temperature and 105 at 700. This is heat resistance. And up to 900 for what type of applications? To make geopolymer toolings. For example, we were involved in the forming of titanium thermoplastic at 950 degrees C and heated press under argon gas. And this has been done for the first prototype of the French fighter Rafale. They made it because we had manufactured the tooling for that. Here we see the geopolymer tooling for two materials that are either advanced composite, organic composite, that are manufactured in an autoclave at 400 degrees C, or advanced superplastic aluminum alloy that are manufactured under heated press at 440 degrees C. For that you need special tools that withstand this temperature without too much expansion, dilatations, and so forth. So we do the painted wood master, cast our geopolymer binder, geopolymer system, and this is the tool on which one manufacture the EPS2 high temperature panel at 400 degrees C. Here same, painted wood master, geopolymer binder mold, on which tool for thermoform aluminum part at 440 degrees C. Again, this has been done for the French fighter program Rafale. Then we have heat and fire resistant carbon geopolymer composites. This is described in my chapter 21. You know now that the carbon epoxy is burning, where the carbon geopolymer is not burning. We had our first applications for racing cars. This one is US and American racing car, Indy cars, that was built by All-American Racer with Toyota in the years 1998-1999. In the US, we were there. We have the exhaust pipe that is going through the carbon epoxy carrossery here. So the body of carbon epoxy body is protected from the heat from the exhaust pipe with a carbon geopolymer jacket around. And since this first improvement, since 2000, all the teams of racing cars and especially Formula One are using these geopolymer carbon that are manufactured by our sister company Pyromelol System, from which you saw the video, and we can claim that Geopolymer is world champion every year. In terms of property regarding fire resistance, fire behavior, what is important is to look at the time to flash over. This is important for the program that is dedicated to cabin fire safety in airplane. We have here the resins, thermosets, these are advanced thermosets, phenolics, engineering thermoplastic. These are organic. You see that after 10 minutes they start to flash over, that is, they start to burn in a fire, even if there is no flame touching them, and geopolymer will never ignite. You may think that carbon geopolymer is expensive because carbon fibers are expensive. In fact, there is a way in reducing the cost. Here we have the flexural strength. Here we have the strain. For e-glass, we have a brittle system, and these are the values for carbon: 525 MPa flexural strength for e-glass, 110. But if we make an hybrid, that is one sheet of carbon and one sheet of glass, one sheet of carbon and one sheet of glass, we end up with a hybrid that has the same strength than the initial carbon. That is, we cut the prices by 2. The problem is that what is good for automobile is not sufficient for aeronautical applications. Racing cars are built to sustain, to run during 25 races in a year. That's one race lasts 2 hours. That means they are built in order to withstand 50 hours at these temperatures. What is requested for civil commercial aircraft, especially around the engines, is more than that. It is 60,000 hours or 10 hours, 10 years fire resistancy or heat resistancy. Geopolymer cement application, geopolymer concrete. I received also a lot of questions dealing with the same topic. This one. What are the highest obstacles of the development of geopolymer cement and concrete? Why did it take 30 years from the invention in 1983-1984 until the successful commercialization in Australia with 100,000 tons of geopolymer concrete for airport? Well, it started in the USA, at Lone Star Industry. I have been asked, but at that time Lone Star Industries was the largest cement company in the Western Hemisphere. And I've been, Lone Star Industries hired me in order to develop a new type of cement, a geopolymer cement, that is known to be named Pyrament. This was in 1983. It was 11 years after I began my research on what is geopolymer. That is, at that time, during 11 years, I had absolutely no knowledge on geopolymer cement and these applications. At the same time, I was appointed at Bayer University, and I created my Institute for Applied Archaeological Science. This is the first geopolymer cement patent filed in 1984, granted in 1985, titled Early High-Strength Mineral Polymer. Joseph Davidovits and Jim L. Sawyer, who was the head of the Lone Star Laboratory in Houston, Texas. The abstract. An early high-strength mineral polymer composition is formed of a polysilate siloxane material obtained by adding reactant mixtures, these are the metakaolins and so forth, with ground blast furnace slag. It was the first time that we added to the regular geopolymer formulation blast furnace slag, a material that was occasionally used at that time by the Portland cement people for their concrete. One discovered the very high property of the material, and its early high strength was very interesting, and the target was the following. Imagine here that in Los Angeles a crew begins placing geopolymer concrete. In New York a Boeing departs. After 1 hour it is strong enough to walk on. After 4 hours it is strong enough to drive on. And after 6 hours it was ready for the weight of a commercial jet. Yes, it works. We started the development in 1983. I sold all my rights to Lone Star Industry in 1989, and the pyramid was manufactured. This first formula for repair, and they were obliged to invent a new type of pyramid because of the standards, and we'll discuss it later. And it was a hybrid, a blended cement involving Portland and geopolymer in order to cope with the standards. They manufactured it until 1997. Then Lone Star had financial problems, not due to pyramid, but to internal problems. And a European company bought the pyramid and so forth and did not continue the production. So it is now in the public domain. For those who want to take it, I can help them. Why so long? Why did it take so long? There are 4 reasons. First, because every alkali activated waste has been called and is called a geopolymer. Second, because of the famous RILEM Committee on Alkali Activated Materials developed by Gianni van der Venter, Professor Gianni van der Venter from Melbourne in Australia, and taken over by Professor John Provis, is now in Sheffield. Why? Because for civil engineers, alkali is a danger. And why? Because of the standards. So we will tackle every point. Why so long? Every alkali activated waste is a geopolymer. This is what we discovered for a reason that I hope I have time to discuss, to develop later, that essentially in a lot of developed countries, they discovered that adding a small amount of NaOH or KOH to any waste hardened the material, in fact, and this is a simple alkali activation of anything, but they called it a geopolymer. And this has been exemplified. For example, here we have a mix of any kind of material, fly ash, mixed with NaOH, mixed with sand, mixed with crushed stone dust, mixed with water glass, and it is called a geopolymer, and this is totally wrong. But this is what has been publicized, and since the results are not good, since there is a lot of drawback, well, it was not a good publicity for geopolymer cement. Geopolymer cement was just alkali activated. Material was also waste. It's not interesting in order to develop structural products. So we had to stop this way of behavior and the way of thinking. Why so long? Because of the RELAM Committee on Alkali Activated Material. What is the RELAM? The RELAM is the International Union of Laboratories and Experts in Construction Materials. So there are a lot of committees and so forth, and this one on alkali activated material has been created by Johnny van der Venter, and today has been, now I guess it's no longer working, but they have another one by John Provis from University of Sheffield in the UK. And I will read you some excerpt from their report that dates from 2014, Alkali Activated Materials, by John Provis, Department of Material Science and Engineering, University of Sheffield and University of Melbourne, Australia, but there's more now in Sheffield than in Australia. Notes on terminology. In the context of this report, the term alkali activated material and geopolymer are at least worthy of some comment. Alkali activated material is the broadest classification, encompassing essentially any binding system derived from the reaction of an alkali metal source. Geopolymers are in many instances viewed as a subset of alkali activated material, where the binding phase is almost exclusively aluminosilicate and highly coordinated. So it is starting here. Confusion. Geopolymers is a subset of alkali activated material. That is, in their mind, high-tech geopolymer, carbon fiber, geopolymer carbon fibers is a subset of garbage, of very bad alkali activated waste. This is the reasoning. The distinction between these classifications is shown schematically in figure 1.2. This is obviously a highly simplified view of the chemistry of concrete forming system. Geopolymers are shown here as a subset, always, of alkali activated material with the highest Al and lowest Ca concentration. So this is the classification. So you have alkali activated material, contain aluminum, sodium, calcium, and then the very small space dedicated to geopolymers. Well, my friends, I also made alkali activated material. I have been asked by companies to develop for them alkali activated Portland cement. It is an alkali activated material. You make a cement, 50% Portland, you add 48%, 47% fly ash, and then some alkali activator, like sodium sulfate, for example, and you have a material that hardens, that is a cement. This is alkali activated material. It is not geopolymer. It has nothing to do with the geopolymer, with the polymeric structure. You cannot compare this geopolymer and take it as a subset of alkali activated material. So I received this email, this question. I am a PhD student in civil engineering interested in producing geopolymer concrete from several byproducts. But in your publications you state that geopolymer is not an alkali activated product, whereas other publications are claiming that there is no difference between the two. I got confused. Well, alkali activated materials are not polymers. They cannot be called geopolymers. Well, geopolymers are polymers. We have two very different systems. To call an alkali activated waste a polymer, a geopolymer, is a nonsense. It is a big scientific mistake to use both as synonyms. Alkali activation is a wrong terminology for geopolymer. What do we have? Geopolymer is a polymer chemistry. We have the polysilate. It is not the calcium hydrate alternative. This is the hydration of the calcium silicate in Portland cement chemistry. You have one monomer, calcium silicate, one Si, that is hydrated with water, and you build a dimer, SiO, and this is the CSH, period. Geopolymer will make polycondensation, polymerization in a three-dimensional network. This is a polymer. I guess it is clear. These are two different fields, chemistry, totally different. But this is what we read, July 2015, in Cement and Concrete Research, published by John Provis, with the help of Angel Palomo and Kajun Shi, Advances in Understanding Alkali Activated Materials. And I look at the reference. When I look at the reference, I have practically more than 50% of the references are dealing with geopolymers. There are others dealing with alkali activated materials, the regular one, but more than 50% are dealing with with geopolymers, and these geopolymers scientific papers are used in order to promote their bad alkali activated cement. And worse than that, you have Provis and Daventa that are the head of the alkali activated material and have published in 2014 this state of the art of the William Committee that I am reading about. And then you see reference number 4, S.R. Bernal, Provis, Durability of Alkali Activated Material, Progress and Perspective, published 2014. 5, Provis and Bernal, so they just changed the name. One is the first author, and then here it is the second one. Provis is the first one, and here they called it Geopolymers. It is the same article, talking about the same results. So they are substituting one wording, one terminology with the other. Angel Palomo and Krivenko are always claiming alkali activated. They are doing alkali activation on different materials. Here you have Van Riesen, Williams, they are cited geopolymers. So if you want to have some scientists to develop an alkali activated material for you and so forth, I recommend that you work with Professor Angel Palomo in Madrid in Spain, because he is a correct person. I know him for 15 years now. There is no problem with him. We have videos that are titled Why Alkali Activated Materials Are Not Geopolymers. They have been put in our internet site, and in August 2014, and since 20 months they have been watched more than 10,000 times. So people are starting to become aware about what is an alkali activated material that are not geopolymers. We put the part 2, this is a clarifying statement on this issue, last year, and after 8 months it has been watched more than 3,600 times. But I continue to always in this William report. It is also noted that the term geopolymer is also used by some workers, both academic and commercial, in a much broader sense than this. This is often done for marketing rather than scientific purposes. So those who are using the wording geopolymer are just doing marketing, publicity. All our development since 1983 is just done for marketing. Nothing, it is not scientific. But this did not prevent Professor Provis from posting this job description in February 2015. We are looking for research associate geopolymer durability, geopolymer. And then you see, experience in working with alkali activated material will be strongly advantageous. In fact, same. For marketing, he's using geopolymer, but for science, he's asking for alkali activation. Nonsense. So, according to Rilem and the associated people that are practically from the Portland cement scientific community, Portland cement, geopolymers is a type of concrete, nothing else, which is wrong. And if we come back to these classifications, geopolymers is a concept, it is not a product, it is not a material. You cannot claim that geopolymers is here. It could be geopolymer cement, but it is totally different. This is a polymer, and these are here just waste, just material that contains a little alkali in it, but I prefer that they do not include in their classification, that do not use the geopolymer in their vocabulary, and they should stay with alkali activated materials and period. Stop. But this is not the end of this type of vandalistic behavior. Because it is a polymer, we must have a geopolymer, a polymer terminology. And this is what I created in 1979 and published it. This terminology is adopted by industry. It is adopted by those who are doing high carbon fiber composite. It is adopted by those who are dealing with advanced materials. But it is not accepted by Portland cement scientists. It is too complicated for them. They prefer to speak about gels and so forth. Polymer terminology is too complicated for them. So I continue the geopolymer terminology. For Provis, always the same in his reports and publishing it. These oligomers are named by some geopolymer chemists as silate, following the scheme developed by Davidovits, although this terminology is not universally accepted within the research community, due in part, so not universally accepted, well, by some people, but this is, they say, well, we are due to, in part, to confusion with the earlier 1952 use of the same word to refer to the salts of the important biomolecule salic acid that was derived from an ancient Greek word meaning saliva. This is what Professor John Provis is writing. Davidovits is wrong. He doesn't know that the Greeks had a word saliva, meaning, and that this word is used by biomolecular scientists, so it is wrong for him to use this name silate. Well, John Provis is not knowing that what I am using is a terminology that is based on geology, because in geology we find for more than 100 years the term silic in rocks. We have silic metamorphic rocks, for example, and since geopolymer are geological analogues, we may use the geology terminology. For example, the oceanic crust is mostly basaltic, and the continental crust is mostly silic, which means associated with granite that contains high amounts of aluminum and silicate. It is related to the high amount of aluminum and silicate. This is logical, and this is scientific. We have also fly ashes. Well, fly ashes, we have fly ash class C and class F, but other classifications are commonly classified into three entities: calcic, ferric, and sialic group. The sialic component results from the percent weight of SiO2, L2O2, 3, and TiO2. These are scientific wordings that are relating to what we are doing. Forget about the saliva of the Greeks and biology. The well-known term Silon, silicon aluminum oxide nitride, for high temperature refractory material, is the acronym of silicon aluminum oxonitrate. It is a scientific logical terminology. The geopolymeric silate term proceeds from the same scientific logic. In fact, we are using for our geopolymer molecule polysilate, polysiloxo, a terminology never used in biochemistry. We shall therefore keep our terminology, use it, and promote it without any restriction. The problem is that John Provis and his friends at the Realm are continuing their vandalistic work and denigrates our development and the scientific terminology associated with geology. They prefer to promote biology, although they claim to work on geopolymers, though they promote alkali activated material. So I am mad of this behavior. For those who want to publish on geopolymer cement or geopolymer concrete, I am recommending not to propose any paper to the journal Cement and Concrete Research, because one of the co-editors is precisely John Provis, and they will be rejected if they use the geopolymer terminology. This happened. There are other friendly journals, such as Construction and Buildings Materials, Applied Clay Science, Mineral Engineering, a Journal of Hazardous Waste, and so forth and so forth. But don't go to Cement and Concrete Research. Stop. Why so long? This is now the third. Since the civil engineers have been told that alkali activated materials are geopolymers, well, they just listen to the word alkali. Oh, alkali activated. For them it is danger because they are confronted with the well-known alkali aggregate reaction, AAR, or the alkali silicate reaction that are deleterious. So you understand why the alkali activated terminology is wrong, because it induces immediately connection with alkali aggregate reaction, despite the fact that if we compare the behavior on alkali activated reaction of Portland and geopolymer, the Portland expand even if we only have 1.2 NO2 equivalent, whereas geopolymer remains intact. So even if this has been demonstrated for 20 years and since ever published, the fact that it is connected to alkali activated waste, alkali activated material, is really a bad publicity for geopolymer cement and geopolymer concrete. Why so long? Because of the standards. When we started in the US in 1983 at Lone Star Industries, there were no standards that could accept this new type of cement. It was only used as a repair material, and for the development of the pyramids they had to cope with a formulation that could be accepted by the standards dealing with Portland blended cement. So they blended the geopolymer technology with Portland cement technology, and they developed the geopyramid. So the standards are the problems. I wrote my answer on this issue that is available on our library as a technical paper number 21. And I will read some excerpt from this paper. The existing Portland cement standards are not adapted to geopolymer cements. They must be created by an ad hoc committee, yet to do so requires also the presence of standard geopolymer cement. To make standards, you need to have standard formulae, standard material. Presently, every expert is providing his own recipe based on local raw materials, waste, byproduct, or extracted. There is a need for selecting the right geopolymer cement category. and I have proposed in my 2012 State of Geopolymerization and Development that I am presenting annually at our Geopolymer camp. I suggested to select only two categories, namely slag, fly ash-based geopolymer cement. Fly ashes are available in the major emerging countries. And the second one, rock-based with metakaolin and geopolymer cement and rocks, special rocks material, and these raw materials are also present in all countries throughout the globe. The properties and the problem with the standards has been also publicized in relation with the making of the airport and the first building made out of structural geopolymer concrete, and published and presented by James M. Aldred. He is a technical director at AECOM. AECOM is a well-known multinational engineering service company that works worldwide. He is also adjunct professor at the University of Northern South Wales in Sydney, and they presented this paper in 2013 at concrete conference in Australia. I read some of what he wrote. Geopolymer concrete has been extensively studied by various universities and is starting to gain acceptance in a range of different applications. Sorry. There are many publications discussing different properties of geopolymer synthesized from different raw materials and activators. Product information sheets and even technical papers may present positive data obtained from different binder chemistry, giving the misleading impression that a specific proprietary material has been comprehensively tested when it has not. Alternatively, papers may also focus on a particular material with poor performance to negatively characterize geopolymer, so is meaning the alkali activation. One common concern raised by designers regarding the use of geopolymer concrete is compliance with the relevant Australian standards, since he is talking to Australians. Standards necessarily develop from the established construction materials and practices which can inhibit the use of innovative materials and procedures. Generally, national standards and codes, which are more prescriptive in nature and explicitly limit concrete to a Portland cement-based binder, are an impediment to non-Portland-based binders being accepted in the industry. For those who are not fluent in English, impediment means a hindrance or obstruction in doing something. So usually national standards and codes contains a prescription that they have to use Portland cement. So that you cannot make any test with geopolymer cement, since they have to be with Portland cement. This is an hindrance and obstruction. European concrete standards AN 206 includes an equivalent performance concept, but there is a restriction that potential binders should comply with European cement standard AN 197, and therefore would technically exclude geopolymers which do not contain Portland cement clinker. By chance, in Australia, they have one standard. It is Australian Standard for Construct Structure AS3 600, does not specify Portland cement-based concrete. The components of the standard are primarily performance-based. In USA, recent adoption of ASTM C1157, performance specification for hydraulic cement, the first version of STM, appeared in 2000, represents an important development in this area. ASTM C1157 simply requires that the cement meets physical performance test requirements no longer Portland necessary. The use of STM is being implemented on a small number of projects to evaluate its effectiveness. The Colorado Department of Transportation has been a leader in the use of performance-specified cements and has used them on a number of highway projects. So standards are starting to change. And they are starting to change, and they will change because of the success, because of the fact that we had innovators and we had entrepreneurs who dared to start this type of applications. Well, whereas all others were waiting that the standard will be changed by whom? By those RILEM committees that are only promoting the Alkali Activated Material. Forget about that. Okay. Talk number 2, principles of geopolymer technologies, fly ash-based geopolymer concrete, 6 basic rules, false CO2 emissions. I'm curious, I would just want to look at the number of participants. Yeah, there are some less. We had 85 at the beginning, we have now 78. It's fine. So, talk number 2 is here. The principles of aluminosilicate geopolymer science have been established in 1976 and have been published, and there is a paper available in the library on that topic, that is the first milestones of geopolymer chemistry. And of course, all the principles of aluminosilicate geopolymer science are depicted in the chapters 1 to 11. So, as I said, we start in 1972, raise the questions: plastic are dangerous, are organic polymers heat resistant? Nature states no, only minerals provide heat and fire resistance. My target was to develop inorganic polymers. I had to look at a low temperature reaction between minerals as if they were organic polymers. That is, low temperature. Remember, at that time, we only knew Portland cement manufacturing or ceramic manufacturing. Geopolymers was not invented. Nobody knew that we could let minerals react at low temperature or even at ambient temperature. Quest for information. Who could provide this information? I had the luck in France to find in Paris at the Museum of Natural History a team of mineralogists that were looking at the reaction that were occurring on the earth with clays, here kaolinite, addition of NaOH, and making of hydrosodalite. Hydrosodalite is a very typical polymeric structure that has very interesting properties. So I published the first science terminology at UPAC Symposium. This is International Union of Pure and Applied Chemistry. The topic: new polymers of high stability. This was the first time that I presented it for solid phase synthesis of mineral block polymer by low temperature polycondensation of aluminosilicate polymers. You understand? Geopolymers are polymers. They are not simple gel or marmalade. So we made what we call block polymers by reacting polysilanols and silates coming from the clays, the kaolinite. And in 1975 we discovered the wonderful properties of metakaolin that results from the hydroxylation of kaolinite. And this happened at 750 degrees C, and this is why we call it now MK750. What was the situation at that time? knowledge from a chemical point of view. We were taking a clay, but we had absolutely no information in terms of its chemistry. What we had at that time for kaolinite was the following. We knew, this is the chemical, not formula, just the oxide that comprises kaolinite. We knew that it is made of, at that time, this is what they claim, and it's still claiming by ceramists, this is the tetragonal sheet, tetrahedras, and this is the gypsum layer, aluminum hydroxide. This is the octahedral sheet. So here all the reasoning was based on geometry. Tetrahedra connected with octahedra. Nothing about their possible chemical reactivity. So I had to, because I am a chemist, I had to write it differently in order to understand where the reactive groups were and where the stable groups were. So I wrote it this way. We had the SiO polysiloxo chain. These are the tetrahedras. And side groups, IL-OH, IL-OH, these are the octahedras. But this is chemically, and I recognize the ALOH, the hydroxyl. And I knew from my chemical background that the aluminum atom was trivalent, chemically trivalent, covalent bonding in that pH, because aluminum is amphoteric. It is either trivalent in an acidic medium or tetravalent in pH, high alkali medium. Here we are in the acidic field and it is trivalent. So I wrote Si2O5, 1Si, 2Si, or 1, 2, 3, 4, and pardon. Oh la la. I go backwards, okay. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen and half here and here. That's my 5 oxygen and 4 OH. This is the unit making kaolinite. For metakaolin, it was worse than that. One knew that we had tetrahedra, to geometry, and here something that could be tetrahedra or octahedra. We didn't know exactly. Still, only geometrical knowledge, no chemical reactivity, even if we knew that what we had experience in our lab, metakaolin was super reactive. So I had to write it differently, because at that time, in 1985, in New Zealand, the team around Professor Mackenzie had discovered with nuclear magnetic resonance spectroscopy that one had geometrically 2 types of aluminum. In fact, we have 3. This is what is called aluminum 5, penta-coordinated, and aluminum 4, tetra-coordinated, and in fact we have also aluminum 6. I said, we have different aluminum environments in the system. This should be related to chemical reactivity that are different. And I started to write these ones. Well, we could have SiO, AlO double bond. Since we are taking the water out, Al is trivalent, and we may write Si2O5L2O2. This is an aluminosilicate oxide, and it is a polysiloxo alumoxyl molecule. This is the aluminum 5 discovered by the team of Mackenzie. And it has been the first time that I introduced this concept, alumoxyl, Al double bond O. This is a totally new concept that corresponds to a very reactive group in metakaolin. Remember, at that time, the reactivity of metakaolin was unknown. This is what we had discovered. In fact, we have two types of aluminum oxide. The one that I called after the intra-aluminum dehydroxylation. Intra-aluminum, that is, we have an aluminum, we have two OH, and the two OH, happening H2O, that is eliminated, and we create this aluminum oxyl L5, Al double bond, aluminum being trivalent. And the second one is, instead of intra, it is inter. That is, we take the OH from two adjacent aluminum and we end up with ALO, 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 and this is the tetra coordinated material. One is more reactive than this one. This is obvious from a chemical point of view. So with this concept, in 1979, we invented our first mineral polymer resin. What is a geopolymer? They are chains or network of mineral molecules linked with covalent bonds. We have siloxo, SiO, SiO-ALO, silate, polysilate, SiO-ALO, siate siloxo, polysilate siloxo, and so forth, with more and more silicon, polysilate disiloxo, phosphate, polyphosphate, phosphate siloxo, phosphoaluminate. This is one very important item. This is the one that is made in acidic medium. And the organosiloxo or the polysilicon, these are the hybrid connected with organic groups, units that are incorporated in the silicon system. Geopolymers are high molecular macromolecules polymers. They are not a gel of unknown structure or colloids or anything like marmalade. If we take the reaction step, the reaction of metakaolin with this double bond is reacting with soluble silicate, and this was the invention of the first mineral polymer resin that we used for the making of various artifacts, either decorative artifacts or for the industry, essentially tooling, molds. Briefly, historical background on the development of aluminosilicate geopolymer. Since previously somebody made the connection between geopolymer and my work on archaeology and the pyramids, there is a fairy tale, a legend that is running in the US. And for example, on my discovery of geopolymer science, for example, a report from the US Air Force laboratory, who was strongly involved in developing geopolymer cement or geopolymer-like applications. They wrote that I first discovered how to make the pyramid blocks, and this is because of that I invented the geopolymers, which is wrong. This is just the opposite. We first invented the geopolymer chemistry and technology because of the knowledge that we acquired through the making of geopolymers, which are geological analogues. We transferred this knowledge in order to interpret, to understand what our ancestors have done. But these are fairy tales and legends, and it is very difficult to cope with this. So if we look at the development, so we have making of zeolites, making of alkali activation slag, making of hydroxylated kaolin and geopolymer. This is for medium geopolymerization in alkali medium. So it started around 1930 with making of kaolin, also in the Netherlands. Then in 1940, strong researchers on the making of zeolite. First alkali activation by Purdon, 1940. Here sodalite. Then 1950s. Zeolite in the US. These are molecular sieves, very important for the industry. And then the first alkali activation cement. This is the Triff cement in the US. And the alkali activation of slag, the Klukovsky, that Then 1960, continuation of the research on the making of kaolin with NaOH and hydrosodalite. And then I discovered this chemistry, made our first work on geopolymer based on kaolinate, and then discovered the property reactivity of metakaolin and started the real genuine geopolymer. The people with alkali activated materials are only relying on this alkali activation slag, Glukovsky, salt silicate concrete, which has been applied in the Soviet Union. So this is their reference, and it shows how low their background, knowledge background can be. In 2008, I've been asked by the International Congress of Ceramics that was held in Verona, Italy, to establish a roadmap of research and development. And this roadmap comprises 16 research topics that are currently studied by various groups throughout the world. First, the polymeric character of geopolymers. Second, polysiloxanate. These are the soluble silicates, water glass that we have to know about. Metakaolin-based, calcium-based geopolymer, rock-based geopolymer, silicate-based geopolymer, fly ash-based geopolymer, phosphate-based geopolymer, organic mineral geopolymer, the long-term durability, geopolymer fiber composites, geopolymer and ceramic processing, the manufacture of geopolymer cement, manufacture of geopolymer concrete, material for radioactive and nuclear waste containment, geopolymer binders for 3D printing. First, polymeric character of geopolymer. We have polymers that have a very precise structure, and we call them geopolymer micelle or nanoparticulates, and they have been first shown by my friend Professor Waltraud Kriven at Illinois University in Urbana-Champaign. And you see here at the end of the arrow you have a small nanoparticulate. These are individual geopolymeric micelle particulates that are 10 nanometers in dimension, 100 angstroms. They have the same dimension as a regular organic polymers. And we are making polymers, and it is obvious that we end up with structures that are related to polymers. If we compare the dimension of the geopolymeric micelle, the particulates, 10 nanometers, this is colloidal silicate, then we have silica fume, and then we have the fly ash, which is a monster. The geopolymer is a nano material. Point number 2, study on polysiloxanate, soluble silicate, water glass. These are the various structures, units that we have in the water glass. We'll see it later. So we have the covalent bonded SiO, and we have to know the molecular structure of the molecules that are in solution. Metakaolin, there are groups that are now are making synthetic metakaolin. There are at least 3 methods. Not by calcining kaolinite, natural, but by synthesizing it. Calcium-based geopolymer, this is the beautiful example of comparing alkali activation of slag with geopolymerization, and I refer to my videos on that topic. Then we have rock-based geopolymer. This is a very important issue. We have silica-based geopolymer. These are the polysiloxo, polysilanol chains that have these structures. We have polysilanols in between silica clusters, and this is used for foundry applications. Fly ash-based geopolymer, we do not propagate the use of alkali activated fly ash user hostile made at high temperature. Phosphate-based geopolymer, these are the aluminum phosphate isomorphs. Organic mineral geopolymer, there are hybrids that contains phenolic, water-based latex, ethyl ester, epoxy, and there are some rules that have been edited, studied by various universities. Here it is Napoli Partenope University. Long-term durability, this Roman cement is providing the silate link. Geopolymer fiber composite, high temperature up to 1300 degrees C, introduction of flax fibers. Geopolymer ceramic processing, this very interesting system that allows the manufacture of high temperature ceramic, cesium-based, lithium-based, gallium, very high temperature resistant material with technology that are really simpler than the one that has been used previously until now. 13, the manufacture of geopolymer cement. If you look at the reduction of the potassium silicate or sodium silicate amount from the beginning, that is since the invention in 1983, 1985 in Lone Star, the first pyramid, we had 50% silicate in it. In the first Geopolymer 50 that was used for the toxic waste and mine tailings waste management in 1987, 50%, and then we started to diminish the system because we understood that we had to diminish the quantity of the silicates in order to start mass production. So we started from 50 to 20 for 100 MPa to 17 for 50 MPa, then for fly ash based 14%, and from fly ash based 40 only 10%. So if you remember my answer to the question, is the liquid more expensive than Portland? You see, when you only have 10%, then it doesn't matter. If it is 5 times more expensive than Portland, then it is still 2 times cheaper than Portland. The target is to reduce to minimum the quantity of the silicate, because this is the one that is the most expensive and the most difficult to manufacture. Geopolymer concrete, so we have the development by Wagner's, this is the Global Chain Institute, and there is myself in one of the room with the slabs here, and here this is the air conditioning devices. And then the airport, 16, number 15, these are the radioactive nuclear waste. We talked about it for Fukushima cleanup. And our 16th geopolymer binder for 3D printing. This is the occasion for you to tell you that at the next Geopolymer Camp in July, we will have a special session for geopolymer 3D printing. I got this question, please explain the difference between chemical valence and coordination. This seems complicated. Since you know now that we are dealing with polymer chemistry, but the problem is that these Portland cement scientists do not understand the differences that exist between a chemical valence and a coordination, that is between chemistry and geometry. I'll show you an example. This is a type of structure that shows what happens with a metakaolin macromolecule, metakaolin product, when it is subjected to alkalination. It is transformed into smaller molecules that will polymerize and so forth and end up with the larger molecule, which is a geopolymer. Fine, correct. The problem is the structure here. This is nonsense. And this is a type of structure that is published in several scientific papers, taken over, copy-pasted in peer-reviewed journals, and the peer reviewers don't see what is happening here, which shows you that the peer review system is no longer working. We know that. There are a few of scientists who are claiming stop this peer review system because it's no longer working, and you have here a beautiful example. What is the problem here? For chemistry, aluminum is trivalent. That is, an aluminum atom is covalently bonded to maximum 3 atoms of oxygen. So we have here silicium in green, silicium, in red the oxygen, and in purple the aluminum. This is the structure of metacarlinite. There is no OH in this structure. Aluminum should be surrounded, covalently bonded to 3 oxygen. It is trivalent. What we have here, aluminum, 1, 2, 3, 4 oxygen. It is tetravalent. This is a nonsense. This does not exist. This structure is false. Worse than that. For chemistry, oxygen is divalent. That is, one atom of oxygen may only be connected to 2 other atoms. And what we have, oxygen connected to 1, 2, and 3. This is chemistry. For geometry, that is based on coordination, it is different. It is the coordination that is surrounded by the oxygen. We don't take any account about the reactivity, the chemical reactivity. We don't care. So, but for metacarline we have Al5, Al4, Al5, and also Al6. So how do we represent this? This is not here. So we have here confusion between covalently bonds and geometrical relation of one atom with the adjacent, with the surrounding other atoms. So if we see it differently, so we have trivalent aluminum. This is the kaolinite molecules with the LOH. So we have Al, O, OH, OH, trivalent. With the hydroxide, the aluminum, this is the inter-dehydroxylation. We end up with the oxide. Aluminum is trivalent, covalently bonded to oxygen, but in fact it is trivalent, but it is in 4-fold coordination. The aluminum is surrounded physically, not chemically, by 1, 2, 3, and 4 atoms of oxygen. It is trivalent, Al3, and the coordination is 4. Don't mix up. If we do it with a different representation, we have the SiO polysiloxo chain and the side groups. We have trivalent aluminum, and here alkalination. In alkaline medium, the aluminum is changed from trivalent to tetravalent, chemically speaking. We have aluminum covalently bonded to OH, 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 oxygen, and the sodium is equilibrating the fact that the aluminum has got a negative charge. So it is tetravalent aluminum that is also tetra-coordinated. So don't mix up. And if we look at what we have under the nuclear magnetic resonance spectroscopy of this metacarline, we have 3 resonances. One that is the most important, this is Al5. This is the one that reacts And this is what we must write in terms of chemical structure. We have SiO, then OAl double bond O. The aluminum is trivalent, one bond to oxygen and double bond, that is 3, but it is surrounded by 1, 2, 3, 4, 5 oxygen. Geometrically, it is penta-coordinated. For the other oxide, aluminum is trivalent, AlO, 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 chemically trivalent, but the aluminum atom is surrounded physically for geometry by 1, 2, 3, and 4 oxygen. It is tetra-coordinated. And then we have this one, this is Al6, then we still have OH group that have not been evacuated during the calcination, the hydroxylated, you had the hydroxylation. So we have the aluminum that is still trivalent in terms of chemistry. One aluminum atom is covalently bonded to one oxygen, one oxydyl OH, one oxydyl OH, trivalent, but physically surrounded by 1, 2, 3, 4, 5, 6 groups, atoms. It is hexa-coordinated. This is Al6. And depending on how the metakaolin was calcined, rusted, depending on the nature of the clay, you may have a different amount of these 3 ingredients, of 3 reactive molecules, and sometimes the OH is relatively high. It can be between 10% by weight and 30% by weight. Is it too complicated for you? You may ask questions on principle of sodium and potassium aluminosilicate science. Fly ash-based geopolymer. This is chapter 12 in my book. I had this question: are there some other activators instead of NaOH? My answer is the following. First, there is no geopolymer activator. We have a reagent, reactive ingredient, or hardener, that involves sodium silicates, in which we have added previously NaOH and CoH. We come back later, because these are sodium silicates or potassium silicates. There's no free alkali in it. So we don't have any activator. Why? Because there is nothing to activate. This is a wrong terminology that is dating back to alkali activation of slag from Purdue in 1940, when he took slag and added 1.5% of NaOH in order to see if the slag was good and reactive. So he said, I am activating my slag because it is inert otherwise. For us, we don't have to activate. The metakaolin is by nature super reactive. You don't have to put NaOH in order to have a metakaolin super reactive. The double bond, the aluminum oxyl group is there. It is, from a chemical point of view, a reactive material. We don't have to activate it. As far as fly ash, the glass that constitutes the fly ash, the 80% of the fly ash are made of glass, and it is the quality of this glass which gives the potential in terms of geopolymerization. The glass is very easy to depolymerize. You don't have to activate the glass it just reacts with alkali, with the sodium silicate, and so forth. These are wording that are totally misleading and wrong. Geopolymerization mechanism follow following steps. We have first alkalination. We introduce alkali, we have an alkaline medium. We don't have to activate anything. Then through this alkali medium, we are depolymerizing the silicates. Silicates are big molecules and they are cut into smaller molecules, depolymerized. Then we have a formation of a gel of smaller molecules, oligosilate. It is a gel because they are in water medium and they are not polymerized. Then we start the polycondensation. That is, the molecules are becoming bigger and bigger, reticulation, networking, and geopolymer solidification. I had another question. What is the significance of using the metal silicate in geopolymer concrete as an hardener with metal hydroxide, and what happens if silicate are not used? Well, if you don't use silicate, then you use what is called the conventional method, that is the alkali activation of fly ash, which requires the dissolution of the fly ash in order to make a zeolite, and for that you need a very caustic NaOH solution, otherwise it doesn't work, and you have to cure at 80 degrees C for 24 or 48 hours, otherwise it doesn't work, and this is a user-hostile system. You cannot put your finger in this slurry, it will burn. User-hostile. And if you look under the electron microscope, what is going on, so you have here 4 different fly ashes, and you have the spheres, they are intact, there is no matrix in between, so the NaOH solution is surrounding the fly ashes and starts to attack the spheres to disaggregate the spheres on the surface, and the result of what is disaggregated, depolymerized or dissolved, will then make the matrix. As a result, in order to get high strength, you need more and more NaOH. Otherwise, you don't have high strength. You don't have enough matrix at your disposal. You have to destroy the entire spheres before having a good matrix. And so, if you want to reach 120 MPa, you must add up to 20 or more NaOH in your system. Crazy. Usually people stop by adding 7% because it is still super caustic and they get 50 MPa. And I have another question related to fly ash. I want to know about the curing process that is used in 100,000 ton geopolymer concrete for airport and world first building with structural geopolymer concrete. As we all know, I repeat, as we all know, this is what I got as question. This geopolymer concrete is heat cured at 60 degrees C with humidity of 56% for 24 hours. So, how this heat curing and humidity is maintained in such a large project at a constant pace of 24 hours? Wow. As we all know. As we all know. Well, as we all know, the one who wrote this email, don't know if it is an email or a question for the webinar, I guess it was an email, has not done his homework, since we have in our geopolymer library freely to be downloaded technical papers that are only dealing with this, how to make, we have our geopolymer cement review that I put on 2013. This is technical paper number 21. We have our GeoAsh, that was our European research project that we run on the making of ambient temperature hardening of fly ash-based geopolymer cement. This is paper number 22 at your disposal. And then we have the technical paper on the geopolymer aircraft pavement. So this is, I am still frustrated by the people who are not doing their homework. We are putting the information and nobody cares. I continue in a scientific paper dealing with alkali activated fly ash, not written by myself. I don't write papers on that topic, but written by another scientist. I don't put his name here. However, AFA, alkali activated fly ash concrete cured at a temperature of 80 degrees C, have no application, and it is practically impossible to use in situ at large scale. Besides, high caustic sodium hydroxide, which is needed for the alkali activation, is user hostile and can present a problem in industrial practice. The only solution, if there is one, is the partial replacement of fly ash with blast furnace slag, which is recommended. That is, develop slag fly ash based geopolymer concrete. That is the geopolymeric method. This is a room temperature hardening. We are making a polycondensation. We are producing a matrix that is interacting with the surface of the spheres. This is a surface chemical reaction. And we make our matrix with the fly ash. We take fly ash between 50 and 85%. This is a lot. We have our potassium silicate solution. You can take sodium silicate solution with a ratio higher than 1.5. This is very mild. We add the blast furnace slag depending on the ratio and the blast furnace slag you have. These are the knowledge that you have to acquire. And then the water. And this is what you get. This is geopolymer cement. Fly ash-based geopolymer cement, user-friendly room temperature hardening. And if you look under the electron microscope, you have your slag fly ash-based geopolymer cement, geopolymer matrix, that is a polycide siloxo, in between the spheres. So you have the spheres, they are intact. Here we have a remain of the slag, blast furnace slag. This is, and then in between we have our geopolymer matrix interacted with the surface of the fly ash. And if we compare 28-day compressive strength, alkali activated fly ash made 60 degrees C 24 hours, and geopolymer fly ash room temperature for different fly ashes. The geopolymer fly ash room temperature hardened material is always better and quite better depending on the fly ash. I continue because what is important is to understand how to handle all this material. So I present the 6 basic rules in geopolymer processing for sodium potassium aluminosilicate to produce polysilates. All successful applications are following each of these principles. So, rule number 1, master the aluminosilicates. I am always repeating the same. For example, if we take fly ash-based geopolymer, chapter 12, master the aluminosilicate means you must to know what you have, what type of mineral you have in your aluminosilicates. For example, I had this question, how to prevent geopolymer pass to crack, for example with fly ash-based geopolymer. It is obvious that the answer relies in your knowledge about what is a fly ash. So you have to know what you have here in terms of principal mineral phases. This is an excerpt of my book, table 12.5. In common coal minerals, coal, that is the constituent that will produce fly ash, is made of carbon, of course, and then quartz, clays, kaolinite, halite, pyrite, Fe2S2, and calcite, calcium carbonate. And these minerals will undergo transformations depending on the temperature of combustion. At 150 degrees C, you get quartz, no change. Kaolinite is transformed into metakaolin. Halite is halite, no change. And pyrite is transformed into FeS, iron sulfide. Iron sulfide is a very, very, very dangerous material in our geopolymer system. It is a retarder. And if you have only 1 or 2% of this guy in a mixed, it will never set. Lime, CaO, on the opposite, is a flash set system. So if you take a fly ash that has been manufactured in and fluidized bed, forget about taking it and making geopolymer, a fly ash-based geopolymer cement. You will end up with a poor alkali activated material with no property at all. Combustion at 1500 degrees C, the quartz transforms into cristobalite, kaolinite into glass plus mullite, the halite into glass plus mullite, and the iron sulfide are transformed into iron oxide, hematite plus glass, and the calcite into glass. And 1800 degrees C, glass, 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 glass. But you have also sometimes, well, the glass, the fly ash that is made in between. If we look at the electron microscope, this is 850 degrees C, you have the remains of the clays here. 850 degrees C, this is the remains of kaolin, this is a characteristical shape. 1250 degrees C, we start to have good spheres. 1250 degrees C, we have remains of biomass here. 1500 degrees C, these are the ideal fly ashes. 1600 degrees C, 1500 degrees C, and 1800 degrees C, these are power plants that are working on a totally different system. They are first getting, this is a gasification of coal. Rule number 2, you must understand their chemical reactivity. Each of these minerals have a different chemical reactivity. Kaolinite, metakaolin, slag, which means that each of these minerals needs a different processing technique in order to enter into geopolymerization. Kaolinite, metakaolin, slag, quartz, silica fume, feldspar, pozzolane, andesite, and so forth and so forth. If you take slag and just look at the oxide composition, depending on the origin, you have different amount of the element. And what is striking is that there are a lot of people that are only looking at CaO, because for them this analysis gives the amount of CaO, and for them they make a confusion between the CaO, that is this is just an oxide analysis, and quicklime or lime. And they make the confusion. For them, slag is in fact a type of lime, CaOH or CaO, that will harden because of alkali activation. And if we look at the minerals that we have in the slag, we have minerals, they are we have one, that is the major part, is what called the melilith. This is a solid solution of galenite. This is a calcium aluminum silicate based, and akermanite, calcium magnesium silicate based, or murphenite, calcium magnesium silicate based. These are minerals, and if you look at their polymeric structure, this is what you have. This is the melilith, galenite, this is the structure, aluminum, Si, oxygen, aluminum, and then the calcium cation in between. It is 2Al, 1Si, silico-aluminate of calcium, dealuminate of calcium. So you need the cation is used to balance two aluminum atoms. Akermanite don't contains aluminum, only silicon and magnesium. And if you subject galenite to alkalination, that is the first step of geopolymerization, it is decomposed, depolymerized into the first small molecule, that is the orthosilate hydrate, SiOAl, and the calcium is here, and the potassium or sodium is here, and it is this molecule that will then interact later. But since we have 2Al for 1Si, and here only 1Al for 1Si, there is precipitation of AlOH3, aluminum hydroxide. For akermanite, alkalination depolymerize the structure of akermanite and provide a small molecule that is calcium disiloxonate hydrate, SiOSi disiloxo, calcium and calcium, precipitation of magnesium hydroxide, and this is the CSH that you find in the alkali activation of blast furnace slag. The two CSH and this one orthosilate hydrate interact and build the first step of geopolymerization, or the last step of alkali activation if you want. Since if you stop here, this is what you get. A mixture of this small molecule and CSH plus aluminum hydroxide, magnesium hydroxide, and calcium hydroxide that are precipitating. These then, for slag MK750 based geopolymer cement, they polycondense with metakaolin and form the first step, the ribbon, the calcium polysilate, and the sodium or potassium polysilate, and the calcium polysilate, sodium polysilate, that further polycondense into a three-dimensional network. So the oxide elementary analyses are useless in terms of understanding what is going on in geopolymerization. Only mineralogy and molecular structure are useful, but nobody cares about this mineralogy and molecular structure. This is why people don't understand what is going on. Rule number 3, user-friendly systems. Chapter 19 in my book. You have in chemistry what is called corrosive and what is called irritant, and what we call hostile systems and friendly systems. Quicklime, NaOH, KOH is hostile. Slake lime, Portland cement, iron slag is friendly. It doesn't burn. You can handle it by hand. Sodium metasilicate is hostile. Slurry of silicate and kaolin is friendly, and any soluble silicate with a ratio, molar ratio higher than 1.45 are also friendly. All others are hostile. So if you want to develop something for the industry, you must choose a system that includes friendly materials. If it is just for fun or just for research because you are doing your research, you may use hostile, but don't claim to save the world in creating a new geopolymer cement in this hostile environment. Rule number 4, master the soluble silicate. Soluble silicate, this is a water glass, period. We just adjust the ratio and not a problem. Wrong. In 1978, when we started to study the making of the first geopolymer by reacting water glass sodium silicate with metakaolin, we had problems because we had reproducibility problems. Between each bottle of sodium silicate water glass that we were purchasing, we had different viscosities. And the problem we had to learn to understand what was going on in terms of makeup, of molecular makeup of the silicates, the soluble silicates, and how to stabilize them. So it is very important to know about the molecular structure of what is in your silicate. And this is chapter 5 of my book. Because you get a mixture of completely different molecules. Some are small, like this one, and some are super big in terms of geometry. And all these will interact totally differently. To show them in a better structural way, this is what you get in your glass, made in the furnace solid sodium glass. These are the structures that you get, complicated structures, and they are dissolved in the autoclave in the factory in order to produce the solution that contains these type of molecules in it. Molecules that are 1, 2, 3, 4, 5, 6 silicon oxygen bonds. These are heptamers. These are the oligomers that I was talking about at the beginning, and they have different shapes. One are linear, one are completely cycled, three-dimensional, and this is a two-dimensional one. And they will interact with the other system totally differently. Rule number 5, replace sodium by potassium, if possible. Chapter 19. Here you have two types of geopolymer cement, potassium-based and sodium-based. Same ratios, molar ratios, just by replacing sodium by potassium. 100% potassium, you reach 90 MPa, 28 days. 100% sodium, you reach 45. That is half of the potassium silicate. Why? Because the viscosity of the two systems is totally different. Sodium silicate viscosity, potassium silicate viscosity depending with temperature. At 20 degrees C, sodium silicate has a viscosity of 2000 centipoise, potassium silicate only 200, 1/10. Or sodium silicate is 10 times more viscous than potassium silicate. Replace sodium by potassium is possible. Today, potassium costs twice than sodium, but in many formulas we use twice less potassium than sodium by weight. Consequently, there is no cost difference. Tomorrow, potassium will cost less once it is mass-produced specifically for geopolymer applications. Using today's cost as the only criteria for selecting materials is a bad idea for tomorrow's development. Rule number 6. Mixing steps must be well defined and always respected. I received a lot of emails and people who are claiming and really discouraged by the fact that when they mold what they have done and put it in the air, after some days they are covered with blooming whitish and so forth, and they are here and say, what it is, why? Well, this is a result of alkali activation, alkali system added to a system that you don't control yields to this drawback, very bad system. That is, people are mixing everything in a wrong way, and we will now show you two videos that shows one, then you get only alkali activated material with all their drawbacks, and the second, when you get the geopolymer cement. So, what is wrong here? I explain. So we come backwards, start again. So we have the fly ash first, then they had NaOH on the fly ash. So the fly ash will take a lot of the NaOH. Then they add the sand. That is, the sand is in contact with the NaOH and will take part of the NaOH on its surface. Fly ash react with NaOH and will be dissolved. Sand, absolutely not, but part of the NaOH will be in between the sand grain and will remain there. Then they add their crushed stone dust, that is a material full of fines, full of aggregates that will also be in direct contact with the remains of the NaOH solution, and they are not interacting with the system, and if there is too much NaOH, they will also take their part and they will also be covered with, but it will not react with the system. And then they add the silicate solution that comes here, outside of anything. It has NaOH is no longer available in order to increase the concentration in the NaOH silicate solution, so that what you end up is a bad mix that contains everything that is not desired. It's fine to make an alkali aggregate reaction product, but not a geopolymer at all. So now I show you how we do a geopolymer cement. This is totally different. We master exactly, we know what we do.
The Davia tutorial describes the manufacture of a high-strength cement. We show here the easiest method to do it. Pour the hardener into the powder. Mix the whole with a mixer or by hand until obtaining a fluid resin. Do not add water. Here we use a vibrating machine for a better hand mix. We weight 80 grams of fillers, which is a mixed sand containing quartz, feldspar and other minerals. Pour the fillers into the resin and mix the whole. The use of fillers is mandatory, otherwise the Davia binder will crack. Unlike Portland cement, which shrinks when used without fillers, Davia cement does not shrink but cracks. Cast the mixture in a hermetically closed mold. For Davia 60, the initial set is as short as 60 minutes, starting from the mixing of the binder, followed by a setting time of 25 minutes, thus totalizing 85 minutes from the initial mixing until the complete hardening of the binder at room temperature. The setting time depends on the room temperature.
So, what is the difference here? We have prepared the ingredient, we have the powder, that is metakaolin, slag and others, in powder form. This is one part. And we have prepared the hardener, that is our special silicate. The hardener are prepared separately and mixed together. And then, this is the geopolymer binder, this is the geopolymer cement, slag, metakaolin-based geopolymer cement, and we add the aggregates, and we end up with a beautiful material. Always first prepare the geopolymer binder, so you have a binder. Do not mix all together, let the geopolymer reaction occur. We are dealing with chemistry. The reactive ingredients must interact in time, step by step. Do not mind mixing the binder in advance. Store it with the fillers in a cold chamber. I had another question. It seems trivial. What is the effect of water in geopolymer concrete? In many research papers, distilled water is used for mixing. But if we use potable water, what is the effect? There is absolutely no effect when you introduce your silicates, sodium, potassium, and the like. You introduce cations in your system, and in fact, if they are using distilled water, it is their problem. We are using potable with tap water, and you can also use sea water if you want, and if you are on the sea shore. There's no problem with having the sodium and the chloride encapsulated within the geopolymeric structure, provided you do it properly, provided you do the mixture according to the rules. I have a small, just 5 minutes to talk about the false CO2 emission value for geopolymer cement concrete published in scientific papers. I have been asked by the major publisher Elsevier to make a critical review of scientific papers that are published by their various scientific journals, and we started with this one in June 2015, and it is online on Materials Today and called Environmental Implication of Geopolymers. So I made a critical review of already published papers, and I discovered that talking about environmental implications, and especially CO2 emissions, scientific papers were making flagrant error in the calculation of the CO2 emissions. And these errors are so flagrant that they demonstrate the fact that the peer review is no longer working. And the problem is that these scientific papers written by renowned people have been cited again by others, those who are against the geopolymer technology, by claiming, you see, geopolymers CO2 emission numbers is a fairy tale, geopolymers cement is not emitting less than Portland, practically the same. And this is a problem, and you will get, first, you can read the paper in Materials Today, June 2015, or you go in our library, there is a technical paper that is called False CO2 Value. The major paper was published in 2011 by a French group of scientists, Environmental Evaluation of Geopolymer-Based Concrete Production, Reviewing Current Research Trend, and you see a methodological flagrant error. CO2 emissions and environmental impact calculated in this paper are wrong and must be roughly divided by 2.6, that is, they are 260% too high. Remember, these are peer-reviewed papers, which means that the peer reviewers are not doing their work anymore. They are not taking the time to read what is here. I have to recalculate everything. And what I have, sure, mistakes, errors. There's another paper published in 2013, Carbon dioxide equivalent emissions, comparison between geopolymer and opacity cement by an Australian team. Here, the results of the CO2 that have been calculated for geopolymer cement are 350% too high. Always calculation errors, wrong assumptions, and so forth. And these papers are taken as example, as cited, and taken for granted by our competitors and people who want to denigrate geopolymer cement and geopolymer concrete. You'll get the entire story in the library and the technical paper number 24, titled False CO2 Value, published in Scientific Papers. To sum up, briefly, first, there is no geopolymer activator. Please learn this. There is a reagent, a reactive ingredient, or a hardener, or a binder. We are using soluble silicate, period. Second, there is nothing to activate. Metacurling is by nature super reactive. Glass is in fly ash is easy to depolymerize. We are starting depolymerization, repolymerization, polycondensation, and so forth. Alkali activated materials are not polymers. They cannot be called geopolymers. Well, geopolymers are polymers. We have two very different systems. To call an alkali activated waste a polymer, a geopolymer, is a nonsense. It is a big scientific mistake to use both as synonyms. Alkali activation is a wrong terminology for geopolymer. Geopolymerization comprises alkalination, depolymerization of silicates, gel formation of oligosilate, polycondensation, reticulation, networking, and geopolymer solidification. So this is the end of my talk number 2. Before we enter into the last question session, I ask you to look at the book if you don't have it. The students have a discount in our shop. Others, the costs are really small. And don't forget, we have our annual Geopolymer camp This is the 8th, July 4 to 6, 2016. This is in Saint-Quentin, between Paris and Brussels, or between Paris and London. This is in northern France, a beautiful city, and it's worthwhile to come. So, thank you for attending this session. I hope we'll see you next time.